Welcome to Lesson 6 of Electromagnetism for Teachers. Last lesson we were studying how an electric current can create a magnetic field around it, and also how a moving charge or current inside a magnetic field experiences a force. This is something called the motor effect, as it is the underlying principle of all electric motors. This lesson, we continue our study of electromagnetism by seeing how a changing magnetic field can create a current in a wire. But firstly, magnetic flux. You already learned about electric flux, which was the total amount of electric field going through a surface of area capital A. In general, you have to integrate the electric field over the whole surface. But if the field is uniform, we can simplify that equation to the equation that phi E, meaning electric field flux, is equal to the electric field times the area times the cos of the angle. It's exactly the same for magnetic flux. So in our earlier work with electric fields, we didn't give it a subscript, but now that we're looking at both electric and magnetic flux, we have to use the subscripts. So we have that phi B is the integral of the magnetic field over an area. And for constant magnetic fields, then phi B is going to be B times A times the cos of the angle. So you can see the amount of magnetic flux through a surface depends on the field strength B and the area of the surface, which is A, and also the cos of the angle between them. So the diagram there shows that when B is at an angle to a plane surface, we only take the component that is along the line of the normal to the surface. So you can see in that diagram that only By, which will be B times cos of phi, will contribute to magnetic flux. Now the unit for magnetic flux is the Weber, capital W and small b. And 1 Weber is the same as 1 Tesla times meters squared. So if we consider a field where B is a constant, so that phi B equals B times A times cos phi. If the field lines are perpendicular to the surface, as on the left, cos phi is a maximum. If the field lines are running parallel to the surface, as in the figure on the right, then no field lines are cutting through that surface and the flux is zero. For in-between angles, you need to use cos of phi. It might help if you imagine the surface as a sheet of paper and the field lines as little darts. The amount of flux then is the number of holes that the darts make in the paper. Look at the diagram and you can see in which case the most number of red field lines are cutting through the black surface. Now, magnetic field must have a direction, so it can cancel, and you have to consider net flux through a surface. Gauss's law for magnetism talks about magnetic flux, and it says that the total flux through any closed surface, like a sphere, must always be zero. That means the total flux going in must equal the total flux coming out. Remember that electric fields are different, and you can have net electric flux out of a surface if there is a net charge inside it. So magnetism is different from electric charge in this fundamental way. Though some grand unified theories and superstring theories predict the existence of magnetic monopoles, or a single north or south pole without the other one nearby, in reality, no one has ever detected any.